Welcome to Electron, and now let's take a look at Stokes' law. What is Stokes' law? Well, it actually has to do with small spherical objects moving through a fluid at small velocities. The reason why we say small velocities is because we want the flow to be laminar, not turbulent. And for that, we need the Reynolds number to be small. We'll talk about Reynolds number in a different video. But what it comes down to, if the Reynolds number is small, that simply means that the object moves slowly and the fluid can move nice in laminar flow around the object as the object is falling or moving through the fluid. So what we want to do here is take a look at this equation. This means the drag on the object, the drag on the sphere that's moving through the fluid can be written as the force sub d, the force of the drag, is equal to 6 pi times, there it is again, is the viscosity, is the coefficient of viscosity of the fluid, times the radius of the sphere in this case, times the velocity of the sphere. Now what we can do with this equation is we can find out what the terminal velocity will be of a bead, like a circular object, like a bead or a marble or something like that, moving through a fluid. And so we can say that at the time that the marble reaches the terminal velocity, the forces, the net force on the object should be 0. Now what are all the forces on the object? So let me use a different color. Well, for one thing, there will be a buoyancy force acting upward. So there'll be a buoyancy force in the upward direction. There'll be the force of gravity, mg, acting downward. And then there's that third force that we haven't talked about before in a situation like this. It'll be the drag force, which is, of course, moving in the opposite direction, or I shouldn't say moving, but is acting in the opposite direction to the motion of the marble or the sphere, and so it would be F sub d. And we then realize that when terminal velocity is reached, the net force will be equal to 0. So at terminal velocity, F sub net is equal to 0. So what we can say then is that the buoyancy force plus the drag force is equal to the weight of the marble. All right. So what we're going to do now is we're going to move the buoyancy force to the other side. We're going to write that the drag force is equal to the weight of the marble minus the buoyancy force. And now we're going to put down what those things are equal to. Well, first of all, because of Stokes' law, we now know what the drag force is. We know that this is equal to 6 pi mu times the radius times the terminal velocity. The weight, mg, but we want to convert the weight into something we can relate to. Let's see here, we know that the density of an object is equal to the ratio of the mass divided by the volume, which means that the mass can be written as the density times the volume. So in this case, instead of mass, we can write rho Vg of the object. This is of the marble, or let's say here, we'll call it sphere, SP for sphere, minus the buoyancy force. And of course, the buoyancy force is equal to the weight of the displaced liquid. In that case, that will be the rho Vg of the liquid. All right. So the volume is the same for both. G is the same for both, of course, is the constant of gravity. Remember, the volume of the sphere is 4/3 pi r cubed. So let's go ahead and factor out a Vg. And that means we have 6 pi times mu times r times the velocity, terminal velocity, is equal to the density of the sphere minus the density of the liquid multiplied times the volume times g. And of course, since I'm out of room, let me come up here. And then we can write this again, and we'll replace v with what v is equal to. So we can write that 6 pi mu r times the terminal velocity is equal to the difference in the density of the sphere minus the density of the liquid times the volume, which is 4/3 pi r cubed, times the acceleration due to gravity. All right, now we should be able to solve that equation for terminal velocity. We could probably simplify a few things. Notice that we have a pi on the left side, we have a pi on the right side. That cancels out. We have the radius of the sphere here, and we have 3 of them there, so that changes from r cubed to r squared. We still have a 6 here. We can bring the 6 to the other side and write 4/18. So now we have mu terminal velocity is equal to the difference in the densities, sphere minus the density of the liquid, times 4/3 times 6, which is 18, times r squared g. Now we can take the coefficient of viscosity, bring it down there, simplify that, and now we have an equation for the terminal velocity. V sub t is equal to the difference in the densities divided by the coefficient of viscosity times 2 over 9 times the radius squared times g. And this is now the equation of the terminal velocity of a spherical object moving through a viscous liquid, where r is the radius of the object, this is the density of the object, this is the density of the liquid, the viscosity of the liquid, and the acceleration due to gravity. And so Stokes' law now gives us two things. It gives us the force of the drag on an object moving through a liquid like that. And secondly, from it, we can calculate the terminal velocity of an object moving through a liquid. Later on, I'll show you some examples where I actually apply these two equations, and so you get more familiar with it. But at least in this case, you can see how, yes, Stokes' law is a very useful law that allows us to calculate several things about the movement of small objects, typically spherical type objects, through a viscous fluid.